Okay, so let's have a look at what we know so far about polynomial functions in a quick review. So we know that we might have polynomial functions given to us in standard form, and here are 6 examples of standard form polynomial equations. Again, standard form is when you can see separate and distinct terms added and subtracted, and in proper standard form, the highest degree on x is written first, and then it decreases in order. So if you look over here, you can see x cubed, x squared, x1, and then no x's. That's proper standard form. Again, you might not always see that, but if you're the one writing the equation, you should always write it in proper standard form. So those are polynomial equations in standard form. We know that it's polynomial because it's a function. There's only one variable called x, and the exponents on x are never anything more complicated than a whole integer that's positive. So a whole positive number, that's the most complicated thing my x can be. So I can't have x to the 1/2 or the square root of x, that means, right? I can't do sine x because that's something entirely different. So really, when you studied linear equations, y equals x to the 1. When you studied quadratic equations, y equals x squared. Those were polynomials. We're just now grouping them all together. So these are examples of polynomial functions in standard form. If you're given a polynomial in standard form, you should be able to identify the following things: the degree of the function, the polarity of the function, and those two things together will tell you the end behavior of the function. And then you should be able to find the y-intercept of the function. So briefly, let me just, the end behavior of a function, because you can do this for any function, not just polynomial, are these two statements. Now it's missing sort of the actual statement about the end behavior, but the rest of the sort of mass sentences here. As x approaches, that's what that arrow says, as x approaches negative infinity. So negative infinity, if you think about the xy axis, x is here. So negative infinity means the left side of the graph. So this formal statement, as x approaches negative infinity, really is saying on the left side of the graph, the function approaches some value. So it's basically a way of saying on the left side of the graph, here's what the function's doing. And then the second statement is as x approaches positive infinity, and of course positive infinity is on the right side of the number line. So this is the right side of the graph. On the right side of the graph, the function is doing this. Now for polynomial functions, the only two things a polynomial function can do is either end up pointing upwards, which means it's heading towards or approaching positive infinity, or it might be pointing down, in which case it is pointing towards or approaching negative infinity. So those are the only two options for end behavior of a polynomial function. Okay, so now let's look at some actual functions and try to make sure we can state these things. So the degree of the function is found by looking at the term that has the highest exponent on x. And again, in proper standard form, that's the first term, but don't always assume it's the first term. Always make sure that that's true. In this case, it's true. I've got x squared, which makes this a second degree polynomial because that degree 2 is the highest degree term. It doesn't matter that there's a degree 1 later on. Irrelevant. This is a second degree because of this exponent 2. To find the polarity of the function, you look at the coefficient multiplied by that highest degree. So the degree 2, x squared, is the highest degree, and it's multiplied by a positive number, positive 3. That means that the whole function is called positive. And again, it doesn't matter what the other signs are. The only sign that matters there is the leading coefficient polarity. And as I said above, you should be able to find the polarity, the end behavior of the function based on this information. So let's have a look at that. So here are the two statements sort of that I've just pasted in here. They're sort of blank. So I have a second degree positive function. I'll just move that over here. So here's what I know. For a polynomial function, I know that I have to write either positive infinity or negative infinity in those two blanks, because it either goes up or down. Well, the polarity of the function tells me what happens on the right side of the graph. So if it's a positive function, it means that it will continue to go in a positive direction forever on the right side of the graph. So we read a graph from left to right. So as you read the graph, the final result is going up. So because this is a positive polarity function, I know that the right side of the graph goes up, meaning the function approaches positive infinity. The other one, the one that talks about the left side of the graph, I look at the degree of the function. If it's an even degree function, so second degree, fourth degree, sixth degree, if it's an even degree function, then these two statements will be the same. So both of the sides of the function will agree. So because I already know the right side goes up, the left side goes up. And that one's pretty easy to remember because you've graphed a lot of parabolas in your day. And you know that a parabola is now considered a second degree polynomial. And we know that both sides of a polynomial either go up or they both go down. They don't disagree with each other. So when you have an even degree polynomial, the two end behavior statements are the same direction, up or down. Sorry, made a mess here. Finally, you should also be able to find the y-intercept of the function. So let me just give myself some space here. So the y-intercept is really easy to find with a standard equation because a y-intercept is found when x equals 0. So I can already write that. If I let x be 0, that's 0, that's 0, and I'm left with 11. So it's really, I'm looking at the constant term, which is positive 11. So the y-intercept is 0, 11. Remember, the y-intercept's a point, so you always write it as a point. So let's make sure we can do this. Here's another standard form equation. Let's make sure we can go through these statements we need to make. Can we tell the degree of the function? So the degree is 17. That's the highest and also the only exponent on x. The polarity, so I'm looking now at the leading coefficient. The polarity is positive, so it is a positive 17th degree, which means I can now write my end behavior statements. So I've just cut and paste them to make it easier. So again, because it's a positive polarity function, the right side of the graph will go in a positive direction. So I know I can put plus infinity there. It's not a very good looking infinity. It's a bit better. Now, because it's an odd degree, then the two statements disagree. It's going to go down on the left and up on the right. And you've graphed enough lines in your day, right? Y equals 2x plus 3 is a first degree polynomial. And we know that a line, one side goes up, the other goes down. They disagree. And that is true for any odd degree polynomial, that the two end behavior statements will disagree. So which one should we do? Let's look at this one. So here I have a polynomial function, x cubed, x4, x squared. All of the exponents are whole numbers positive. What degree is it? Well, the highest exponent is exponent 4. So it's not written in proper standard form, so I have to find it. This is a 4th degree polynomial. Doesn't matter that that's a cube and that's a squared, irrelevant. This is a 4th degree polynomial. The coefficient in front of x4 is positive 1, so it is a positive 4th degree polynomial. And behavior statements, oops. So because we know that this is a positive 4th degree, right, because the leading coefficient was positive, then this second statement, the right side of the graph, would go up. And because it's 4th degree, it's even degree, just like a parabola, so both sides do the same thing. In this case, they both go up. And then finally, to find the y-intercept, I can sub in x equals 0, but then I get 0 plus 0 plus 0, So the y-intercept is just at 0, 0. So just having standard form gives us a lot of information, but we still can't really make a really great sketch of the function. And that's why we want to focus more time on looking at a polynomial function in factored form. So here's an example of a factored form polynomial. So instead of having separate and distinct terms added and subtracted, I have it in factored form. So you could certainly imagine expanding and multiplying and collecting like terms and getting back into standard form. Or if you start with standard form, obviously you have to factor it to get factored form, which we'll learn how to do soon. I mean, you already know it for some of them because of grade 10 and 11. But let's look at this factored form polynomial. So first of all, I can tell it's still a polynomial function because all of my x's are just plain old x, meaning x to the exponent 1. And if I started to expand and collect like terms, I would still just have x to some positive number. So it's a polynomial function. We should be able to find the degree. And basically, you can find the degree by looking at, if I were to expand, I would end up at some point multiplying x times x times x. And that would give me x cubed. And there's no way to get any more complicated. Like that's the maximum number of x's at any point that are going to be multiplied together. So I can tell that this is a third degree polynomial. And the polarity of it, well, if I were to do that math, like the expand and collect like terms, I know I would do x times x times x, but because of this, I would actually end up with negative 2x cubed. So it is a negative third degree polynomial, which means we can write the end behavior as x approaches negative infinity, the function approaches something, and as x approaches positive infinity, the function approaches something. So this statement we can start with, as always, because the degree of the function tells us what the right side of the graph does. In this case, it's a negative polynomial, which means the function goes down on the right side of the graph. Because it's a third degree, that's an odd number, 3 is an odd number, then the two sides disagree with each other, so the other side must go up. We should also be able to find the y-intercept. So these are all the things we could find in standard form, but now we're finding them in factored form. So we know that a y-intercept is when x equals 0. So I'm just going to sub 0 in for all of my x values. So I would have 0 plus 1, 0 minus 2, 0 minus 5. So I would have negative 2 times 1 times negative 2 times negative 5, which is negative 20. So the y-intercept is the point at 0, negative 20. So those are all the same things that we can find in standard form, but the advantage of factored form is we can also see where the roots of the equation are. So roots is another name for y-intercepts, or sometimes they're called zeros. And we know from our work in quadratics, for example, that an x-intercept is found when y equals 0, or in this case, output is 0. So just to remind ourselves what that means, if I want the output to be 0, then I need to figure out what x values make that true. Well, because it's in factored form, right here, I can see that if x was negative 1, then this bracket would be 0. And if this bracket's 0, the whole thing equals 0. So one of my x-intercepts, or roots, is at negative 1. There's another one here, because if x equals 2, 2 subtract 2, this is 0. And then no matter what else is happening, 0 times anything is 0. So I've got another x-intercept. And if I look here, I can see that if x equals 5, I've got another solution, so another root or x-intercept. So now, what we like about factored form is we can tell everything we used to from standard form, but we now also have the roots. And what that allows us to do is to make a reasonably fast, but reasonably accurate, in terms of important points, sketch. So it's not a graph. I'm not trying to make a beautiful graph with grid paper and rulers. I just want to sketch. I want to see the important features. So I know that there are roots at -2, 2, and 5. Again, notice I'm not really like carefully measuring or scaling. I'm just labeling what I know. Now, what else do I know? I know that the end behavior tells me that on the right side of the graph, so hold on, this is the right side of the graph, it should go down. So I'm just going to draw an arrow to remind myself to go down. And on the left side of the graph, it should go up. And then all I'm going to do now is try to go through. I mean, I missed that one a little bit, but you can see why it's just a sketch. It doesn't matter. Pretend that went through there. But that's really roughly what it looks like. And we can see the important roots, and we can see the end behavior. And the other thing that we can see is I calculated the y-intercept to be -20, and I can see that I definitely have a negative y-intercept. So the other thing I do is I label that -20. And that is a sketch of a polynomial function in factored form. It shows all the important characteristics. I do not know how high the bump is because that's a calculus feature, but all the important characteristics are there. So I'll just do another one quickly with you. This is a 1, 2, 3, 4th degree polynomial. And if I were to multiply x times 2x times x times x, I would have 2x to the 4, which is positive. So the end behavior, as x approaches -infinity, the function approaches something. And as x approaches positive infinity, the function approaches something. So because I have a positive function, then I know that the right side of the graph will be positive infinity. And because I have an even degree, I know that the two sides agree. So both sides of this function are going to go up. I can calculate the y-intercept. Again, if you let x equal 0, sub 0 here, 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 and here. Well, because I'm subbing 0 here, that's really 0 times, it doesn't matter what else is there. So I know the y-intercept is 0, 0. And then I can find the roots. So I'm just going to go and look at where my roots are. So x equals. So this is a root of 0. This is a root of -5/2, which is -2.5. And if you're not sure how I got that, remember it's whatever makes this bracket 0 is my root. So I have 2x plus 5, and I want that to be equal to 0. So 2x equals -5, and then divide by 2. So, and then I've got a root at -1, and I've got a root at 4. So those are my roots, and now I can make a reasonable sketch of this function. Boom, boom. So I have roots at 0, -2.5, -1, and 4. I know that the function goes up on both sides of the graph. And now I just have to sort of go through all of my roots. So don't forget 0 is a root there. So root, 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 and there we go. And you can see that I passed, the y-intercept is 0, so I don't have that extra y-intercept, positive or negative nature. So that's mostly it, with one exception, and that is that not every polynomial function has such nice normal roots. There is something called higher order roots. Basically, a higher order root is a root, let me give you an example, where there is an exponent on that binomial for the root. So we know that if this was a function I was studying, we know there would be a root at -2, but that tells me that it's a higher order root. In fact, we call it an order 2 root. And what that means when I'm sketching is this. It bounces off the root instead of passing through it. So a normal root is I just draw through it. Like I just draw like I did in the last two examples, make sure I go through the root. But if it's a degree 2 root, it actually goes, It goes to the root, it doesn't go through it. It bounces off of it. Yeah. Now that it actually bounces off in a similar way if you had a 4, order 6, order 8, any even degree exponent, it's also going to bounce off. It's just that, the shape of it for like an order 2 versus order 4 isn't something that we could really analyze or show or get correct the different subtle shapes without a computer. So we're only really going to deal with squared. Just know that if you do see a 4, 6, 8, 10 order root, do exactly what you would if it was a squared. Bounce off. We might also see some roots that are order 3. So for example, if you have a binomial in your factored form, here I have a root at -1, but it's not a normal root, it's an order 3 root. Then what happens on the graph? Well, it does this, which is it goes to the root, and it goes through the root, but it does what I call slow down at the root. So you can see here, this is a normal root. It just passes right through it, like inconsequent. It's just like aim for that, go through it. But an order 3 root is go to that root, but slow down. Like there's this weird S pattern that you should see, right? It sort of snakes around it. I'd say it slows down. And again, that's the same sort of thing that would happen if you had a degree 5 or degree 7 or degree 9 or any like odd high order root. It would also slow down. And again, the different subtle shape between what a 5th order versus a 3rd order, we can't tell that. We're not computers. So any higher order odd root, you just do this snake S pattern, or slow down as I like to say. So let's put that to the test, and we're going to look at this. We're going to make a sketch of this. So first of all, I want to state the degree. So I've got x squared times x. So don't forget that exponent is important. This is x squared times x. There's no other x's, so this must be a degree 3. What would be the leading coefficient? Well, if I did do x squared times x to get x cubed, I would also have to multiply by that. So this was what my leading coefficient would be. So it is a negative 3rd degree. That means I can write my end behavior statements. I'll just paste them again, even though that messes up the screen for a second. There it is. So what I have is a negative function, which means that the right-hand side of the graph is going to go down. And because it's an odd degree, the other side does the other thing. So they always disagree. The y-intercept, so to find the y-intercept, we're going to let x equal 0 and see what we get. So if I sub 0 in here, put a 0 here, put a 0 here. Don't forget about that, because what I have is negative 3 times 3 squared times negative 1. And don't forget bedmiss, I have to do 3 squared first. So I have negative 3 times 9 times negative 1, which is 27. So there is a y-intercept at 27. So now I can start to sort of, and then my roots, sorry, almost missed my roots. Where are my roots? So I have a root at x equals negative 3, and that one is an order 2 root. So we just like to, when we list our roots, if they're higher order, we just sort of write, by the way, this one's special. And then I also have a root at 1. And you can tell that you haven't missed anything. Because this is order 2, I've got 1, 2, 3 roots on a 3rd degree, which makes sense. And now let's put all the pieces together into a sketch. So I've got a root at negative 3 and a root at 1. Now this is a bouncing root, so I have to remember that. My end behavior. So my end behavior tells me that I need to be up on the left side of the graph and down on the right. So I need to This one here, I need to go to that root but bounce off it, and then just pass through that root like normal. There's my function. And then I can also say, well, I have a y-intercept of 27, and that makes sense because I have a positive y-intercept. All right, one more quick example. This is a 1, 2, 3, 4, because of that, 5, 6, 7, 8, 9. This is a 9th degree polynomial. Again, just to double check, remember we're looking at the exponent on that bracket. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 9th degree polynomial. Is it positive or negative? Well, positive, 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 positive. So it's positive x to the 9 multiplied by 2, so it's still positive. So it is a positive 9th degree. Let's look at our end behavior statements. By the way, you notice you always write the end behavior statements in this order. So even though we tend to think about this one first, we always write the negative one on top. Same reason we put things in order as we've seen so far throughout the course. So this is a positive function. So the right-hand side of the graph is positive infinity. It's an odd function, so this would be negative infinity. They disagree. Let's find the y-intercept. So the y-intercept is when you let x equal 0. Maybe I'll give myself a slightly smaller pen here. So if I sub 0 in for x, I've got 4. Here I've got 2 to the exponent 3. Here I've got negative 1 squared. Here I've got negative 3 cubed. So obviously this is something you'd probably just do in your calculator. I've got 2 times 4. I'm doing my exponents first because you have to. Negative 1 squared. Negative 3 cubed is negative 27. So the y-intercept is whatever that multiplies to be. 2 times 4 times 8 times 1 times negative 27 is negative 1,728. So it's a good thing we're not trying to make like proper graphs with like normal scales, because I don't care about any other y value. I only care about that one. So there's my y-intercept. And now we can talk about roots. So the roots of the function, I have a root at negative 4. I have another root at negative 2. And that is an order 3 root. I've got a root at 1, which is order 2. And then I've got a root at 3, which is order 3. All right, so I'm going to have some, bumps and bounces and slowdowns. All right, negative 4, negative 2, 1, and 3. I know that based on my end behavior, I have arrows, down. This should be negative, and that should be positive. And then this is a bouncy root. And these ones here are slowdown, so I just want to hopefully remember that. So first I'm going to just go straight through my first root. Straight through, don't do anything. Now I'm going to have to turn around and go through this root. But remember, I need to slow down a little bit. So see how I just sort of snaked that around? So I didn't just go through it, I spent a bit of time there. Now I need to turn around, and I need to bounce off of that root. Bounce off. And then I need to turn around and go through that root, but I need to slow down, slow down. Oh, and usually, when you've done it correctly, you can be like, oh, that makes sense. There's, if I bounced when I sort of slowed down, I won't match my end behavior arrows. And then the other nice thing to check is that my y-intercept is negative, and yes, it is. My y-intercept is negative 1728, I think it was. So we always label that. It's a way of checking. Okay, so that's sort of the first bit of this unit.